In previous sections, we were looking at the normal distribution, and if we were given a standard normal random variable, let's say x is distributed normal mu sigma, we would standardize it by taking and finding a z-score, x minus mu all over sigma, and this would mean that I now have a value, standard normal random variable, distributed normal 0, 1. Remember, 0 is our mean, 1 is our standard deviation. Now this is for the case when n equal 1. So this is important to remember. This is for when n equal 1. Well, what changes in this particular example or this particular section is I still have an underlying distribution. X is distributed normal mu sigma, but now my standardization changes because I have a sample size greater than 1. So it's not just equal to 1. So n is greater than 1. What happens then is I'm looking at the sampling distribution of x bar. I'm looking at the averages of my sample size. So x bar minus mu divided by sigma over root n. And you have to be really careful about how you enter this into your calculator, and we'll look at that in a little bit. Well, what ends up happening here is after I standardize that, then z is distributed normal 0, 1 again. But again, this is for the case when my sample size is greater than 1. Now we also have another case that we look at. If my underlying distribution is unknown, I don't know if it's normal shaped or not, but I do know its mean and its standard deviation. If n is greater than 30, then what happens is z is approximately equal to x bar minus mu sigma over root n. So this should be approximately equal to, let me fix this, approximately equal to. Now again, what we have when we have this z-score, then z is approximately distributed as normal with a mean of 0 and a standard deviation of 1. So this is when n is greater than 30. But if my underlying distribution is normal, it doesn't matter what my sample size. It'll always be distributed normal 0, 1 when I talk about my average and my sigma over root n. Now also what we're talking about here in this particular case is this is called the standard error of the mean. So standard error of the mean. And the mean, of course, is my value for x bar. So in the problems that we're going to be looking at in this section, it's really important to know something about sample size. If my sample size is 1, meaning I'm just looking at an individual person, then I have to assume that my underlying distribution is normal in order for me to work. If my sample size is distributed normal underlying, it doesn't matter what my sample size is. It's still going to be distributed normal 0, 1, and I can still use my normal tables. If my underlying distribution is an unknown shape, then the sample size has to be greater than 30 in order for me to use my normal tables. So the most important thing is to keep track of sample size here. So let's go ahead and run through a few examples so we can start to see what happens here. So for our first example, assume that women's heights are normally distributed with a mean of 63.4 inches and a standard deviation of 2.2 inches. Now usually you're not going to be given the mu equal and the sigma equal. I'm just writing that in here just to give you a quick reminder about that. Now part A for this one says if one woman is randomly selected, so if we know it's one woman, we're kind of back to that case where n is equal to 1. Find the probability that her height is less than 64 inches. Okay, so let's go ahead and summarize kind of what we have going on here. Women's heights are distributed normal with a mean of 63.4 inches and a standard deviation of 2.2. We have a sample size of one woman. We want to know that this randomly selected woman, find the probability her height is less than 64 inches. So women's height is less than 64 inches. Okay, so if we go ahead and draw our picture with our normal distribution, we go ahead and mark where the mean is. So our mean is right here at 63.4, and that comes from right up here, mu. And there, of course, is sigma. So 64 inches is somewhere to the right of that. Now, we're looking at the less than case. So we're looking for this shaded area. So this is our women's height. So this is the W scale. Now I would like to convert these all to Z-scores. Of course, our mean always converts to 0. Now to convert this value of 64 to my Z-scale, what I would do then is I'd have Z equal X minus mu over sigma. So Z equal X, in this case is 64, minus 63.4 all over sigma, which was 2.2. And let's go ahead and see what we have for our Z-score here. So in the numerator, I have 64 minus 63.4, which is 0.6, over 2.2. And I get 0.2727 repeating. Because my normal tables only go out to hundredths anyway, I'm just going to round this to 0.27. So up here, what that means is my standard score, and I'm looking for the probability that the Z-score is less than 0.27. Remember, 0.27 is the number of standard deviations we are above the mean with the value of 64 inches. And it's important to know this definition. Okay, so Z was 0.27. So that's the Z-score here. Now there's a couple different things that we can do. We can, of course, use our normal tables, and then we can also use our calculators. So let me go ahead and grab a copy of our normal tables and pop it on the screen, and let's look this up. Okay, so we're looking up at 0.27. So here's 0.2. And then we come clear across until we're underneath the 0.07, and we have 0.6064. So that probability would be equal to 0.6064. Whoops, wrong notes. So that's the answer to this problem. That's also the shaded area right here, 0.6064. So we know that the probability that the next randomly selected woman has a height that's less than 64 inches is about 61%. Now we can also do this on your calculator. So remember, that's under second DISTR. We want to go to normal CDF, which is our second option there. Now our lower endpoint is going to be something like negative 100,000. And then my upper endpoint would be this 0.27 if I want to use a mean of 0 and a standard deviation of 1, or because I'm already given these values, I could look up 64 inches. Now if I use 64 inches, I need to use the mu and sigma that are given to me right here, 63.4, and sigma is equal to 2.2. So you can use the 0.27 if you'd like, but then you have to change your mean and your standard deviation. Okay, let's go ahead and look up this probability. So if we do this on the calculator, we get a close solution. It's not exact, and of course we found this that happens before, is when we use our calculator, we tend to get a little bit different solution, because if you notice here, I'm going out to negative 100,000, and I'm looking at 0.27 repeating as opposed to just 0.27 from the table, so they will be slightly different. But you should be able to report either one of these values, and usually they ask you to round to 4 decimal places, so here this would round to 0.6075 because the 6 would raise the 4 to a 5. So that's for part A. That's looking at one individual woman's height. Now for part B, let's go ahead and say if 48 women were randomly selected. So again, used to be n equal 1, now n is 48. Let's find the probability they have a mean height, not just a single height, but a mean height. Again, we're still doing the same less than 64 inches. Okay, so let's go ahead and look at our setup here. From above, women's heights were distributed normal with a mean of 63.4 and a standard deviation of 2.2 inches. But now we have more information. That was for n equal 1, but now we know n equal 48. So for n equal 48 then, the average women's height, so W bar, is distributed exactly normal because our underlying distribution was normal. My mean doesn't change, but my standard deviation does. It changes to 2.2 divided by the square root of 48. Now, the reason the standard deviation changes is because I'm getting more and more information. And as I get more and more information about the data, you know, if I have a sample of size 48, the variability or the spread will diminish. Whereas if I just had one piece of information, there's a lot of room for variability because that one piece that I pulled out of the population may not have been very representative. So what I'm doing then is I'm finding the probability that W bar, okay, because we're looking at the averages, has a mean height less than 64 inches. So I'm going to still go and standardize this and come up with a standardized score. Let's go ahead and draw our picture out. The picture really doesn't change here. I still have a normal distribution, although it's a little less wide than it was in the last problem because my variability is decreased. Here's my value of 64. I'm still trying to find this area to the left. Now this is for my women's height scale. This is my W bar scale. And then of course I want to find my Z scale. The mean always standardizes to 0. Now let's go ahead and standardize Z. Z equal X bar minus mu sigma divided by the square root of n. Now we have to be careful again how we enter this into the calculator, and we'll kind of look at that here in a second. Now why is this X bar when the last problem was just X? It's because we have a sample size of more than 1. So let's go ahead and fill out what we have here. Z equal X bar. That's my average of 64 minus my mean, 63.4. Sigma, which was 2.2, divided by the square root of 48. Okay, so let's go ahead and calculate this. And again, you have to be careful how you put it into your calculator because of this denominator. So what I'm going to do is in the numerator, I'm going to have everything in parentheses, 64 minus 63.4, close parenthesis, divided by, open parenthesis again, 2.2 divided by the square root of 48. And you have to have all these parentheses in, otherwise what ends up happening is things don't flip properly and you end up multiplying instead of dividing and vice versa. So let's go ahead and tuck this in here and see what we get. We get 1.89. So if we're going to use our normal tables, that's what we would have here is that value of 1.89. And then of course we'll also look to see how to use your calculators to look up this probability as well. Okay, so our tables go to the hundredths place, so we'd round 1.8895 to 1.89. So my probability of Z here is the probability of Z is I'm 1.89 standard deviations below the mean. I'm to the left of the mean. So 1.89 standard deviations, and I'm looking for the area to the left. So this value standardized to 1.89. Now if we look up above, the same value standardized to 0.27. Now what's changed here is here I divided by 2.2. Down here I'm dividing by a much smaller number, 2.2 divided by the square root of 48. And because I'm dividing by a smaller number, my numerator is still the same. What ends up happening is my Z-score ends up being larger. So let's go ahead and pop open our normal tables. We'll look up 1.89. So 1.89 clear to the end here, 0.9706 is what we get from the normal tables. And again, that's 0.9706. So if I have a random selection of 48 women, the probability that their heights are less than 64 on average is about 97%. That's a big number. 9706. So that's my solution here. Okay, let's go ahead and look at that same output using the normal CDF function on your calculator. So we go second DISTR, normal CDF, Now my lower is still going to be that negative 100,000. My upper will still be 64. My mean is still the same, but now my standard deviation should be 2.2 divided by the square root of 48. Okay, so now we're going to see what the probability is that the average group. Okay, and let's go ahead and see what we get here for our value. Paste that in. Now we get something pretty close. Again, the calculator readout is a little different. It's a little bit more exact. And so what we get here for our output then is 0.970588. But notice, if I round this to 4 places, I'd get 0.9706. So those are pretty similar problems. So again, the only thing that changed here was whether my sample size was equal to 1 or if it was not equal to 1, and then I had to change the formula that I use. So looking at sample size is going to be kind of the key factor here. It's the first thing that we want to identify. Okay, let's go ahead and look at another example. In this example, we're going to be using women's heights again, but we're going to be changing the mean a little bit in the standard deviation. So let's suppose women's heights are distributed normally, so we know the underlying distribution is normal, and we have a mean of 64.6 inches and a standard deviation of 2.1 inches this time. So the information is changing here a bit from the last example we did with women's heights. Now for part A, it says if one woman is randomly selected, so n equal 1 woman is randomly selected, find the probability that her height is between 64.3 and 65.3 inches. Now remember, we're using W to represent women's height. So if we draw a quick picture here, we know that the mean is 64.6, and I'm looking for the probability that I'm between 64.3 and 65.3. Now between means the area shaded right here. So what I'd like to do is I'd like to standardize this score so I get a value for the number of standard deviations I am above and below the mean for the 64.3 and then for the 65.3. So this is my women's height scale. Now I have my z-scale. Now remember, the mean always standardizes to 0. Now if I look at 65.3, again I'm looking for the number of standard deviations I am above the mean. My sample size is 1, so I'm just going to be using z equal x minus mu over sigma, because of course n equal 1. So I have 65.3 minus 64.6 all over sigma, which was 2.1 from up here. Okay, let's go ahead and see what this value turns out to be. 65.3 minus 64.6 divided by 2.1, and I get 0.3 repeating. So my tables are only good to hundredths, so I'm going to go ahead and round this to the nearest hundredth. So this is 0.33 standard deviations above the mean. Let's go ahead and standardize my other value. Again, my sample size is 1, so I use x minus mu over sigma. So I have 64.3 minus 64.6 all over 2.1. Now this one should be negative because I'm below the mean, so I have 64.3 minus 64.6 divided by 2.1, and I get negative 0. Oops, my calculator cleared out. Let me try that again. 64.3 minus 64.6 divided by 2.1, and I get negative 0.1428, but my table is only good to hundredths, so I'll round that to the nearest hundredth. So I'm 0.14 standard deviations below the mean. So this means the probability that my z-score is between 0.14, negative 0.14, and 0.33. Now the way that we're going to find this, again, we find the area to the left of my higher score, and I subtract out the area to the left of my lower score, and then of course what I'm left with then is the area between. So this looks like 0.33, looking that up, minus phi of negative 0.14. So let's go ahead and grab our tables. We're going to look at 0.33 first. So 0.33, 0.30123, 0.6293, And then of course we'd look up negative 0.14 next. Negative 0.14, 0.4443. And we'll subtract those to find the probability. 0.6293 minus 0.4443. 0.185 is what I get when I subtract those. So that 0.185, that's this area. That's the shaded area. That's my between. Remember, I got that by taking the area to the left of 0.33, and that's going to be 0.6293, and then subtracting. And of course, these are my standardized scores. Now we can do this on your calculator as well, using the normal CDF function. So that's second DISTR. Oops, let's try that again. Second DISTR, normal CDF. Now here, my lower is going to come from right over here. It's going to come from 64.3. So I have 64.3. My upper is going to be 65.3. And my mean is the 64.6 in the middle. Now my standard deviation is just going to be 2.1. My sample size is equal to 1, so I don't have to really worry about dividing by n, because I'm not looking at an average, I'm looking at an individual value. So let's go ahead and enter this and see what we get and compare our values. Okay. Didn't copy very good. Let's try that again. This one will be better, be a little darker, easier to read. Okay, so if we compare our values then from our calculator, and again if we round to the nearest 3 places to match these 3 places, I'd get 0.187. Now if your calculator asks you to go to the nearest 4 places, of course you'd have to make sure that you carried it out to the nearest 4 places if it indicates such. And it does make a difference whether you're using your normal tables or your calculator, but it should accept both solutions. Now for part B, what we're going to do is we are going to change the fact that we're actually looking at a group of women. So in this case, if 10 women are randomly selected, and so what that means is my sample size has changed now. It's no longer n equal 1. We want to find the probability that that group of 10 women has an average height and if you see mean height, average height, that means the same thing. And let's do between the same 2 values. So let's do between 64.3 and 65.3 inches. So to start setting this one up, we know our underlying distribution. Actually, we didn't use X, we used W for women's heights. We're normally distributed, and for this example, the mean was 64.6 inches and the standard deviation was 2.1 inches. But something changed here. I have a sample size of 10 from up here. And if I have a sample size of 10, the average height of the groups of 10 women has a normal distribution of 64.6. and the standard error of the mean of 2.1 over the square root of 10. Now we don't want to take this number and get a decimal approximation. We want to leave it as 2.1 over square root of 10 so we don't have any sampling error, or we don't have any error because of our rounding. So to work from here, we're looking for the probability that my average height is between 64.3, so W bar, and 65.3. So this really changes. I have a lot more information. I have a group of 10 women instead of just 1 woman to try and find the probability. So when I get done here, I'm going to standardize these values. So I'll have a z-score, and then of course I'll look up 5 of each of these z-scores and then find my actual probability. Now what doesn't change is the picture. It's a little narrower because my standard error is decreased, but my mean is still 64.6. I'm still between 64.3 and 65.3. And I'm trying to find the shaded area because it's between. So I'm going to find the area to the left of the top number. I'll subtract out the area to the left of the bottom number, and I'll be left with the actual area here. So this is my W bar scale. What I need to find is my Z scale now. Now my mean always standardizes to 0. Now in this case, I'm going to use a different formula. I'm going to use X bar minus mu sigma over the square root of n. So I'll have 65.3 minus 64.6, which is my mean. Sigma, and if we look up here, sigma was 2.1. So I'll have 2.1 divided by the square root of my sample size. Is 2.1 divided by the square root of 10. So let's go ahead and enter this in your calculators very carefully. Need to make sure we have parentheses around my numerator. 65.3 minus 64.6, close parenthesis, divided by, and make sure you open these parentheses up again, 2.1 divided by the square root of 10. And again, you have to be really careful about how you enter these. Square root of 10 in parentheses. So let's see what I get here for my z-score. So it looks like for my upper z-score, I get 1.05. Okay, so that means this value is 1.05 standard deviations above the mean. And the reason I'm only taking 1.05 is my normal tables are only good to the hundredths place. Let's go ahead and standardize our other score. So again, my sample size is more than 1, so I need to use this formula right here. So I have 64.3 minus 64.6, 2.1 divided by the square root of 10. Okay, let's go ahead and plug this into our calculator very carefully again. These sometimes can get tricky. So we have 64.3 minus our value of 64.6 divided by 2.1 divided by the square root of 10. Now this should give us a negative number because I'm below the mean, and it does. This says that I'm about 0.45 standard deviations below the mean. That's what the negative value means, is my score is below the mean. So again, our normal tables are only good to the nearest hundredth, so let's go ahead and just round this to the nearest hundredth. Okay, so it looks like I have everything here. What I need to do now is look these up on my normal tables. Now my probability statement would be negative 0.45 less than z less than 1.05. So I'm looking up 1.05 on my normal tables and negative 0.45. So if I grab my normal tables and I look up 1.05, here's 1.0, 1.05, 0.8531. And I'm going to look up negative 0.45, negative 0.45, I have 0.3264. Now if we subtract those, what we have is that area between then, and that area directly corresponds to probability. So 0.8531 minus 0.3264, I get 0.5267. So this area is a little smaller than our last one. Actually, it's larger. Sorry, 0.185 was our last one. So this is actually larger. So that's this area. So the probability that a randomly selected group of 10 women have an average height between 64.3 and 65.3 inches is about 0.5267. Let's go ahead and grab our calculators and do this with the second DISTR option under normal CDF. My lower endpoint is 64.3. My upper endpoint is still 65.3, and I'm getting those numbers from right here on my table, also in my probability statement. My mean is still 64.6, but my standard deviation now is 2.1 divided by my square root of my sample size. So divided by the square root of 10. Okay, so let's go ahead and look at the probability that we get there, and we'll compare them. So here, we're pretty close. I have 0.5267 with my normal tables, and then down here with my calculator I'd have 0.5284, because the 5 would round the 3 up to a 4. So you can see that the probabilities are pretty close there. And my math lab should accept either one. So we've looked at one that was a less than, the area to the left. We've looked at a problem that was the between case, and let's go ahead and look at some other types of problems as well. For this example, instead of looking at heights, we're going to be looking at blood pressure. So let's go ahead and suppose blood pressure is normally distributed, and for this particular group of people that we're looking at, the mean is 114.8 and the standard deviation is 13.2 mmHg. mmHg are the units that you measure blood pressure in. So what we're going to look at here are some different cases. Now we already know if our sample size is 1, what we need to do is we need to go after a different formula. So for this example, if a person is randomly selected, now a person is our key word here, so this means n equal 1. So if a person is randomly selected, let's go ahead and find the probability that their individual, not the average, but that their individual blood pressure is greater than 110. Okay, so again, this case n equal 1, and that makes a big difference. So blood pressure is normally distributed with mean equal to 114.8 and a standard deviation of 13.2. Again, n equal 1 here, so that means I'm using z equal x minus mu over sigma. So if we draw a quick picture here, actually let's write out our probability statement first. Blood pressure is greater than 110. That was given to us right here. Blood pressure is greater than 110. So what's going to happen here is I'm going to get some sort of a z-score, and then because I'm looking at the area to the right, I'll have to take 1 minus phi of that z-score. So we'll fill that out here in a second. Let's go ahead and put up a quick curve sketch though to help us visualize what's going on here. So our mean is 114.8. I'm looking at greater than 110, so 110 is down here, and greater than would be this area to the right. Okay, so this one's a little bit different because I'm looking at a value that's going to produce a negative z-score into the right. So this is my blood pressure scale. Let's go ahead and look at my z-scale. The mean always standardizes to 0. Now let's go ahead and see what z is doing here. Z equal x minus mu over sigma. So 110 minus 114.8 over sigma. Now sigma in this case is 13.2. So z is equal to, for this value, 110 minus 114.8, so I should get a negative answer, divided by 13.2. I get a negative 0.36 repeating, but my tables are only good to the nearest hundredth, so I'll round this to the nearest hundredth. So this is negative 0.36. So I'm looking at the probability that my standardized z-score is more than 0.36 standard deviations, negative 0.36 standard deviations below the mean and above. Okay, so now remember, our tables give us the area to the left. So when we look up our table value, it's going to give us this little region right here that's blank. Our total area underneath the curve is 1. And if I look up the z-score of negative 0.36, it's going to give me this shaded area, so I'll need to subtract that from 1. So let's go ahead and take 1 minus, and let's grab our tables, negative 0.36. So we'll be looking on the left here. Negative 0.36. So So I'm looking up 6 right here. So I get 0.3594. Now 0.3594 is not the answer. This area right here is 0.3594. So this area is going to be 1 minus 0.3594. And I get 0.6406 for my probability. So that's the probability that the next randomly selected person, a single person, n equal 1. Let's go ahead and use our second DISTR using our normal CDF. And it looks like my lower bound here is going to be 110. My upper bound is going just to be a really large number. My mean was 114.8. And my standard deviation was 13.2. So let's go ahead and compare this to what we have when we work with the normal tables. And again, they should be similar. I don't expect them to be exact. And with our normal tables, I have a probability of 0.6406. Using our calculator, which is probably a little bit more accurate, is 0.64193. Now remember, we usually want to go to the nearest 4 places, so that's 0.6419. So it's pretty close to what we got when we were working with our normal tables. So we've looked at a less than case, we've looked at a between case, and we've looked at a greater than case on how to use these particular values. Now, the reason that when we're working with these that we can use this is called the central limit theorem. And again, the central limit theorem back from our original discussion basically says that if my underlying distribution is normal, like this one was, then what I know is the sampling distribution of a group of blood pressures chosen from this are normal as well. So that's going to allow me to answer problem B underneath this. So for problem B, we have 5 randomly selected people. So for 5 randomly selected people, what is the probability that that average of those 5 randomly selected people have a blood pressure greater than 110? So find the probability of their mean. You could say mean or average blood pressure is greater than 110. Okay, so let's go ahead and look at our setup. Now, to get started, remember blood pressure was distributed normal with a mean of 114.8 and a standard deviation of 13.2. And that was for just my general population. Now what's happening here though, I have n equal 5, which means that the average blood pressure is distributed normal, 114.8, and then the standard error would be 13.2 divided by the square root of 5. Now what allows us to say this is the central limit theorem. Now we usually abbreviate that CLT. So it's the central limit theorem that allows us to say this. Okay, without the central limit theorem, to say that the underlying distribution is normal, then the distribution of my averages is also normal. I really couldn't say much beyond this. So we're looking for the average blood pressure in my group of 5 people being greater than 110. So the process is still the same. So I'm looking to standardize this, and then once I standardize it, because I'm looking to the area to the right, I have to take 1 minus phi of that value evaluated. Let's go ahead and do a quick curve sketch, because I think that always helps show what's going on here. Now remember, my mean is 114.8. 110 is my value I'm looking at here, and these are for my average blood pressures. Now I'm looking for greater than, so this is this shaded area. And then I'm looking at my z-scores. The mean always standardizes to 0. Now here, z equals x bar minus mu sigma over root n, because I have a sample size of 5. So x bar is my 110, my mean is 114.8, and then my sigma value is 13.2 divided by the square root of my sample size, which is 5. You on our calculator, you have to be very careful about how you enter this. So we would have in parentheses 110 minus 114.8, close parenthesis, divided by, open those parentheses again, and we have 13.2 divided by the square root of n. Now this n in this case is our sample size was 5. Okay, so we get negative 0.81311. Now our normal tables only go out to the nearest hundredth, so it only does any good to round this to negative 0.81. So that's what I'll record here is negative 0.81. Okay, so this score is negative 0.81. So I'm looking for the probability of being greater than negative 0.81. Because I'm looking to the right, I need to make sure I subtract that probability from 1. So now let's go ahead and grab our tables and look up negative 0.81. So from our tables, here's negative 0.80, negative 0.81, which is 0.2090. So if we look at our picture, this is 0.2090. That's not our answer. Our answer is over here to the right, which is 1 minus 0.2090, because the total area underneath the curve is 1. So if I know one part of the curve, I can find the other by subtraction. So I get 0.791 here from my normal tables, or my probability. Now I can also go after this using your second DISTR function. So second DISTR, normal CDF. My lower value is 110. I can see that from my picture, and I can also see it from my probability statement. My upper is this very, very large value. My mean is 114.8. My standard deviation is 13.2 divided by the square root of 5. So that's changed. Let's go ahead and calculate the value, and we'll do a comparison with what we got with the normal tables. Now remember, you can do these problems either way. I think it's a good idea to use both methods, so that way it's a good way to check your work to make sure you don't have any mistakes. So we can see we get 0.7919 if I round this to 4 places, which is very, very close to what we have here. So what did allow us to do this? Well, up here, the central limit theorem allowed us to do this because my underlying distribution was normal. Then I know something about the distribution of the averages being normal as well. Now we haven't run into any problems about where I don't know the shape of the underlying distribution, and you won't for this homework set. But remember, that brings into mind the case where we have to have a sample size larger than 30 to approximate the normal distribution. But again, I didn't see any in your homework set, so if we run across any of those in a quiz or something like that, I'll make sure that we take a look at that. As usual, if you have any questions, make sure you stop by my office, bring your questions to class, or you're welcome to stop in the Math Center as well. Good luck.